In this video, I want to introduce to you the concept, the paradigm of functional programming, and I want to show how you can do it in Python. So in Python, there is, of course, a lambda expression, and there's five or six functions that I need to call out to you that's built into the language that you might want to take advantage of if you want to try the functional programming approach. Before we get too deep into what these are, let's talk first about what a function is, what functional programming is, and then we'll get into the lambda expression and other things like that. What is a function? We've talked about this before in the video on functions, or I introduced functions to you, and I tried to approach functions explaining to you that there's two kinds of functions that you need to keep your mind on. One is the traditional kind of function, which might access global variables. It might access and modify the objects that are passed into it, and the results of the function may not be consistent each time it's called. Okay, and then there's the concept of a pure function, and I'm going to give you a new word, idempotent. This means basically every time you call it, it does the same thing. It doesn't change its behavior. Calling it once or calling it a million times will get you the same thing. Okay, a pure function, if you use pure functions, you can greatly simplify the logic of your code. They're easier to write, they're easier to understand, they're easier to test. There's all kinds of great things about pure functions. But when it comes to functional programming, pure functions almost become a necessity. It's really difficult to do functional programming with anything but pure functions. So what are pure functions? What does it mean to be pure? It means that it doesn't change, it doesn't access global state. So no global state. It doesn't modify global state, so it doesn't access it, it doesn't modify it. It also doesn't change the arguments. So you haven't yet been introduced to objects in Python that are mutable, but if you pass a mutable object to a pure function, it will not modify it at all. Also, the results depend entirely on the arguments. So this is because of these two things, because you don't change the global state and the objects don't change, then you know that if you call it with the same objects again and again, you're going to get the same results. Okay, so and again, I encourage you that if you can write a pure function, please write a pure function. In fact, find an excuse to write pure functions if you can. Okay, let's talk a little bit about functional programming now. So Python at its core, like many languages you probably know, follows the procedural programming paradigm. By paradigm, I mean a way of doing things. Like, so the paradigm defines to you like the standard practice, like how you approach a problem, how you think about a problem, and all those kind of things. And so in the procedural programming paradigm, you think of programs like a recipe. You give specific instructions on what to do and how to do it. You have a global state that you're modifying, okay? And you often think in terms of how things are changing over time, rather than what methods or functions you're calling to accomplish the purpose or derive the result you want. Functional programming turns this on its head. So in functional programming, one of the signs that you are able to do the functional programming paradigm is that functions are a first-class value. And what this means is, just like you can pass numbers around, you can pass functions around, okay? So it's based on the old lambda calculus. Lambda calculus is a mathematical concept that was developed early in the 20th century. And it describes a way to think about programs and a way to program using very simple rules of logic. And if you get a chance, I would encourage you to take some time to learn lambda calculus. It's not really that difficult, especially compared to some of the other math subjects you've been exposed to by now. Okay. In functional program, recursion is used a lot. So I've introduced you to the topic of recursion already. Don't forget the lessons you learned about recursion. It will save you some time. In fact, recursion is the only algorithm, the only method you can use to solve certain kinds of computing problems, especially when it comes to trees. In functional programming, there's several optimizations you can use. For instance, in recursion, we can use something called tail recursion. So let me list some optimizations we can use. So we have tail recursion. And what tail recursion says is if the result of the function is itself a call to another function, then before it calls that last function, it removes its own frame from the stack. And then it puts the call to the next function on the stack. And so in this way, you can call functions recursively as many times as you want. The stack size won't grow. Okay. Tail recursion is one optimization. Another optimization is that it can refuse to, it doesn't have to call functions if the result isn't needed. So if the result not needed, don't call. Okay. And another optimization is that if two functions don't depend on each other, so like the result of function A is not used for function B, then you can do it in parallel. You can run A and B, A then B, or B then A, or you can run them at the same time. If a pure function is called twice, so if you call 2 times with the same parameters, you can remember the result and return that instead. This is often called memoization, M-E-M-O-I-Z-A-T-I-O-N, and it's a fairly powerful technique. It can greatly increase the speed of your program, especially if you're calling the same functions over and over again with the same arguments. A good example where memoization really shines is if you're doing a recursive Fibonacci sequence, because you're calling Fibonacci not just on the previous value, but also the value before that. So it has kind of a exponential behavior if you don't do memoization. You can also do something called inlining. So what inlining does is if you have a function, like let's say you have the function add, and it takes 2 parameters, A and B, right? If you call add with, let's say, 1 and 3, what it can do is replace that, instead of actually calling add, replace that with what add would have done, right? And even then you can just, in the compiler can say, oh, you're just taking the constant 1 and adding the constant 3, that's always going to be 4, and just replace it with 4. And so this code that you wrote here, add 1, 3, the function is never called. It just gives you 4 right directly. And so that's an optimization that you can do as well. There's a concept that you need to be aware of. You've already been introduced to it, you just don't know what it's called. I'm going to call it lazy evaluation. Okay. What lazy evaluation means is you do not actually call the functions that would give you the result until you actually need that result, right? So for instance, if I called function A and then called function B with the result there, and then called function C with the result of B, right? Don't actually call A and actually call B and actually call C, but instead return some kind of placeholder that remembers how it would actually get the result if it wanted it, right? And then when I told the placeholder, hey, I actually need that value, then the code will go and run A and then run B and then run C, okay? And we've already been exposed to this in the form of iterators, okay? And lazy evaluation is great is because if you can somehow postpone or defer actually evaluating the values, then a lot of the optimizations that functional programming gives you, for instance, if you don't need the result, you never evaluate it. If 2 functions are called to generate the result, but they're not dependent on each other, you can call them in parallel or out of order or whatever you want to do. Many of those things can happen, including the memoization too, right? So you can memorize the result and only call it exactly once, right? So iterators are is a example of lazy evaluation in Python. And I'm going to give you some more examples here as we go through the lambda expression and some of the built-in functional functions. I should note though that even though Python definitely doesn't support many of the optimizations that functional programming languages do support, it doesn't mean that you should just abandon functional programming altogether in Python. In fact, many of the ideas that you learn from functional program are directly applicable to Python and languages similar to Python that aren't first-class, functional programming languages but are similar. So if you do study functional programming, when you get a chance, I do encourage you to dive a little bit deeper in this topic and learn more about how things actually work in this universe. And I will say that sticking to pure function calls as much as possible will greatly simplify your code, reduce the complexity, make it much easier to understand. And you'll even be able to identify patterns just by looking at your code. Like, when you're doing math, you can find simplifications and optimizations just by looking at the math expression. And because your code will be so much simpler and easier to understand, you'll be able to find optimizations yourself and pre-optimize your code. Let's talk about lambda. So in lambda calculus, lambda is what you might call a function, right? The idea is that lambda takes parameters, it applies an expression to those parameters, and there's all kinds of things that goes about that. So in Python, lambda is an expression. It starts with the word lambda, L-A-M-B-D-A, and then you have an expression list, just like you have for functions, right? And then you do a colon, and then you have immediately following that an expression. You cannot put the expression on a new line after it. It must be on the same line. Of course, you can use like a backslash to break up the line if you need to. Okay, so this is the same as for def. When you call a lambda, this expression returns a callable, what you might even call a function. Okay. When you call it, it's just like calling the function, except it returns the expression, whatever that is. Okay. Let me give you some examples of lambdas. So this one will add two numbers together. This one will take an arbitrary number of arguments and tell you how many there are. Okay, and this one will take a single argument and raise it to the third power. Okay, these are all examples of lambdas. Now typically we don't assign lambda to variables. Sometimes we do, but typically we don't. We just put them in place where we need them as they're called. And typically we only use very simple expressions like this. Okay, it's rather easy to specify pure functions using the lambda expression. One of the reasons is it only allows expressions, and so statements that typically would modify the state or thing like that are not allowed. But you must be careful that the expression doesn't contain function calls that are not pure. Let's look at some of the built-in functions that will aid you in doing functional programming. The first we're going to look at is called filter. Okay, filter takes a function and it takes an iterable, and it returns an iterator. This is an example of lazy evaluation. And what filter does is it applies the function to each item in the iterable, and if the result of the function is true, then it adds that as a result to the iterator. Okay, if it's false, then it keeps going until it finds one that's true. All right, for instance, we might do something like this. We might say filter, and we're going to find every item that is odd. So A, where A divided by 2 will give you a remainder of 1. Okay, so this is the modulo operator. We're taking A, dividing it by 2, and looking at the remainder. And if it's equal to 1, then it's odd. Okay, and then we're going to apply this to, I don't know, let's take the reversed range up to 100. Okay, and this will give us some iterator. And when we call next, let's say I is equal to the result of that. So we call next on I. It's going to take the range up to 100, reverse that. So the first item is going to be 99. 99 divided by 2, remainder 1. So the first result is going to be 99. And then when we call it again, it should give us 97, right? So it'll call it on 98, but find that this isn't true. And so it'll call for the next one and then give you 97. Okay, and so on and so forth, all the way down to 1. All right. The next function I want to look at is called map. And what map does is it takes a function and it can take iterables, one or more iterables. Okay, and this will also return an iterator. All right, and what the function does is, what this function map does is it takes each of these iterables, it calls next on each of them, and then it passes those as a series of arguments to func. And then func then the result of the iterator will be the result of that func, right? Let me give you an example. Let me use a different color this time so that you can kind of see the code separate from the example. Okay, so we are going to take map lambda of x, and we're going to raise that to the third power, x star star 3, and then we're going to do range up to, let's say, 5. Okay, and so that returns an iterator. So let's store that iterator in I, and we say next I. And so it goes through each of these iterables. So in this case, there's only one, so it takes range, gets the next value, which is 0, and then passes that into this function. So lambda of 0 is 0 to the third power. That should give us 0. The next, we call it again. Now we're going to get back 1. 1 raised to the third power is 1. Calling it again, we get 2. 2 raised to the third power is 8, and so on. Okay. We can also call it with multiple. So we can say I is equal to the map of, let's just say, lambda x comma y. I don't think the parentheses are allowed here. Excuse me. So no parentheses. We'll say x plus y, and then we'll have 2 iterables. We'll do range up to 10, and we'll do range starting at 10 and going up to 20. Okay. And so when we call next on this one, this should give us, well, the first range will give us 0. The second range will give us 10. 0 plus 10 is 10. And if we call it again, it will give us 1 plus 11 is 12. All right? It's not too complicated. The next one I'll mention is called zip. What zip does is it takes a series of iterators, or iterables, and it combines them together. Again, this returns an iterator. Let me actually show this to you so you can see what I'm writing. So zip takes a series of iterables and returns an iterator. What it does is it iterates through each of these iterables at the same time and joins them together into a tuple. So for instance, if we called zip, let's use a different color here. Let's say I is equal to the zip of range 10, range from 10 to 20, and range from 20 to 30. What this will return for the first element will give you a 0, 10, and 20. And if we call it again, we'll get 1, 11, 21. And if we call it again, we'll get 2, 12, and 22. Okay, so it's just iterating at the same time through each of these elements and returning a tuple that's joined together of those things. All right. The functool modules has a lot of interesting functions that you might want to look at. Some of them are a little bit complicated. You might be struggling to find a way to use them. One of them that is important is functools.partial. Okay, and what you do with this is you call it with a function, and then you have all the args that you would pass into that function. Okay, and what this returns is another function, a partial function. And so this result, if you were to call that result of the partial function with additional args, then it would be like calling this original function with all of the args specified in partial and all of the args that you've added in. So let me give an example of that. Let's say we took functools. So we did import functools. You have to import it. And we did functools.partial on our add function. And we're going to specify the first thing we're going to add is 3. Okay? And this is going to return a function. And if we call this function with 5, then it's going to call add with 3 comma 5, and it's going to give us back 8. Okay? This is useful. Oftentimes you have like a function that you want to call and you only have a few parameters, and you later on you'll find the rest of the parameters, or you want to just modify one of the parameters multiple times, and so you create a partial and then you call it with just the modified parameters. It's pretty useful. I'm always excited when I get a chance to use partial. Another one that's super useful that we've already covered because we've actually written a version for ourselves is functools.reduce. And what this does is it takes a function, it takes an iterable, and then it takes an initializer, which I believe defaults to none. And just like the reduce function that we wrote, it'll go through the iterable, apply the function to the running result and the next value of the iterable, and remember that, and then at the end it'll give it back to you. And so an example of this could be functools.reduce. We're going to do an add of the series 1, 2, 3, and we're going to start with 0. Okay, so this should take 0 plus 1 plus 2 plus 3. So it adds 0 and 1, and then it adds the result of that in 2, and it adds the result of that in 3. So that should give you 6. Okay, pretty useful function. Anyway, this is a very brief introduction to functional programming. I can only go so far in the time that I have allocated. And I wanted to get you introduced to these functions. I wanted to get you used to the lambda expression, and hopefully to whet your appetite for learning more about functional programming and lambda calculus. Guys, have a great day. Take care. Bye-bye. Thank you for watching this video on the theory of Python by Real Physics. Be sure to subscribe and ring the bell, like and share this video. You can find me on Discord or support me on Patreon. Links are in the description below. Thank you so much. Have a great day. Bye-bye.